Welcome to our second screencast on the abstract data type of queue. So remember, the principal characteristics of the queue is they're first in, first out. They try to be fair. If you arrive at the end of the queue, you get processed before the person behind you or the item behind you. They have a size. We can know how many items are in the queue, but we cannot access things in the middle of the queue. So you can only add things to the rear, and you can leave from the front. You can't leave from the middle. You can't cut unless you have a priority queue. But we're talking about non-priority queues today. And so here's the queue interface. As recall, we can have two methods for adding something to the end or the rear of the queue. We have add, which throws an exception if there's a problem, or offer, which does not throw an exception. It returns false if it cannot add E to the end of the queue. We have two methods for looking at what's at the front of the queue. We have element that throws an exception if the queue is empty, and peak that returns null if the queue is empty. And we have two methods for removing things from the front of the queue. Remove something from the queue, but throws an empty queue, no such element exception if the queue is empty, and poll will return null if the queue is empty, and lastly, size returns the number of items in the queue. So last time we talked about a linked implementation. We're now going to talk about an array implementation, and as we have talked previously in lists and stacks, we use an array to store the items. We have quick access to the items. The problem is the array is often larger than the number of items in the queue for efficiency, and it's more complicated because we need to keep track of the front and the rear of the queue, and we have to do a little bit of math modulo the size of the queue, or excuse me, size of the array, to be able to go around and be more efficient. And that adds a little bit of complexity, but it's not the same as having your private interclass node. It's a different kind of complexity. So in our array queue, we keep track of where the front of the queue is, where the rear is, how many items are in the queue, and we have our array of data to hold the items in the queue. Now, so to initialize our array queue, we need to initialize all four of our member variables. We're going to first create the array. Initialize front as to where the first item is, where the front of the queue is. Initialize the rear, and then initialize the size. So we'll create our array of objects. In this case, I'm making size 8, just so that it fits on the slide. And then I cast it to my generic type E. I then initialize the front. So the front is going to point to the first item in the queue. Now, when the queue is empty, front could be -1, but I'm just going to leave it at 0, and we'll check to see if it's empty before we try to access something, because if it's empty, I can't access the item at front because there is no item in the queue. I initialize the rear to point to the last item in the queue, and since there's nothing in the queue, I might as well just make it data length -1. So that's the last item, but since it's empty, I can't look at that, and I can't have access to the rear anyway. And then I initialize the size to 0 to allow me to decide that it is an empty queue. So now let's talk about how we add something to the rear of the queue. So our first method is the add and the offer, and the add method throws an exception, and the offer method does not. So we're going to add E to the rear of the queue, increment the size, and return true. But since we're in the array implementation, we need to check to see if the array is full. And if it is, we're going to reallocate to grow the array. Or if we want to throw an exception because we have a fixed size, that's where we would throw the exception. Then we update the rear to point to the next empty spot, because rear normally points to the rear of the queue. We then add E to the rear of the queue, increment its size, and return true. So if size is data length, we're full. If we were going to throw an exception, we would throw it here. Otherwise, we're going to reallocate to grow the array and copy the items from the old array into the new array, and then update front and rear, and we'll talk about that in a few slides. So the first step is, once we know we have enough room in our array, we update rear, because rear was pointing to the last item in the queue, so we need to update it by adding 1. And then to make it circular, we mod it by the length of the array so that we'll go wrap around. And we're going to do a lot of this something +1 mod by the length of the array to go make this a circular. We can now add the item to the rear. So now the rear is pointing to the last item in the queue. front is pointing to the first item in the queue. We have to increment our size to get that correct. And now we can indicate successfully returning or successfully adding the item to the end of the queue. So we return true. And then we say, what's the big O of this? Well, it's the big O of 1 because the only thing would be the reallocate has a thing, but we don't do it. We amortize the reallocate over every n times we call add. So it has a big O of 1. And so now let's add something to the rear with the queue not being empty. So we check, do we have room? Yes, we do. So we again update the rear to be pointing to the rear item. So now we can assign the item to the new rear, and then we update our size to be 2, and then we can return true, and we have successfully added 2 items to our queue. And you can see how, as we get to the end, rear will wrap around, and later on we'll see how front could wrap around by using the modulus math. So now the offer method is going to return true if it's added, otherwise it's going to return false. It's not going to throw an exception. So we could, instead of having we could copy the code, or we can try to do the add, and if there's an exception we can return false. So we're going to try to return add. If it succeeds, then we added it. If it doesn't succeed, it throws an exception, we just need to return false. And because the add method is big O of 1, and this is just calling that, this is a big O of 1 operation, and that's the the offer method. And so the next thing is, how do we look at the front of the queue without updating the front of the queue? We don't want to change it. We're just peeking, or we're looking at the inside. And the element throws an exception. Element method throws an exception if the queue is empty. If it's not empty, we return the front of the queue or the head of the queue. And so we check to see if it's empty by saying if size is 0. If it is, we should throw a no such element exception. And then if it's not, we return the data at front. So we're not updating front. We're just saying this is the thing at the front of the queue. And the big O of this operation is 1 because it's just basically accessing an array. Now for the peek method that doesn't throw the exception, again, we can try to see if element returns something, and we can catch that exception and return the special value of null. So we try to return element. If it succeeds, we return the value at front. If it doesn't succeed, if there's an empty queue, we'll return the special value of null. And because the element call was big O of 1, this is a big O of 1 operation. And then the last pair of methods are the remove and pull method. The remove method throws an exception if the stack is empty. So we need to check to see if it's empty. We need to remember the value at front. We're going to update front. We're going to decrement the size, and then we finally return the value that was at front before we updated the front. Very similar to the linked implementation where you got to remember the value before you update the pointers. Same thing here. You can consider that front is sort of like a pointer to the item, so you need to remember the item before you move front. So we check to see the size. It's not 0. If it is 0, we throw our exception. Then we need to remember the values, so we just grab the value out of data front. We update front, and again, we're doing the +1 mod the data length, so that would give us the circularity. And then we decrement the size, because now there's only one item in our example. And then we can return value to say that was what was at the front. We've now updated our queue, so front is pointing to the front of the queue, rear is still pointing to the rear of the queue, and we have one item in our queue. And the big O of that, again, is 1 because we just accessed the array and did some math. And now the pull method is similar to the remove, except for if there's an exception, we turn null. So we try to remove. If it throws the exception, we will return null. If it didn't throw the exception, we would have returned what was at front, which would have been bar. And now we're done. And the big O of 1, same, because we called remove, which is big O of 1. Otherwise, we just did a catch. Size, we just return the size. And here's the reallocate. So it's got a slight twist in the reallocate is because our front and rear move around, so we don't know exactly where they are. But first we create a new array that's bigger, twice as big as the old array. We assign J to front because we want to go through front and possibly loop around and put all of the data that was in the old position, and we want to move it to the new thing starting at 0, going to size -1. So that's why we're doing J is going around the old data, and we're putting it into 0 through size -1. So now that we've copied all the data from the old data array to the new data array, we now need to initialize front and rear. So front is going to be at 0 because that's where our first item is. Our last item is at size -1. And the data gets assigned to the new data. So we've now copied the old array over, and then we put it back. So now we have our correct thing. The size did not change because we didn't actually add anything. We just made the array bigger. We have an iterator on our array queue. We keep track of where we are, and we have to keep track of how many items we've returned. Because it's circular, we can't say, oh, we got to the end of the array. We need to keep track of how many we have returned. So when we initialize the iterator, we say the index is front because that's where we are, and we're going to go around. And then the has next is just saying, have we seen all the items in the array or in the queue? So count is less than size, it has a next. Once it's size, we have seen them all, and we're done. And now the next just says, as long as it has a next, if there is no next, we throw no such element exception because iterators throw the exception if there is no next and you call it next. Again, we remember the data at where we were. We need to update where we are to the next one, and that's the +1 mod the length of the array. We increment our count saying we've returned something, and then we return the item that was next. And that's our iterator. So the second kind of queue, an additional kind of queue that I want to talk about briefly, is called a deck. It's a double-ended queue. Get it? Double-ended queue. And so you can add to the front, you can add to the rear, you can remove from the front, and you can remove from the rear. So you can insert and remove from both ends. You still can't get to the middle items, but you can insert and remove from the end. So you have an offer first, offer last, add first, add last, peek first, peek last, get instead of an element first, element last, it's get first, get last. You have your poll first, poll last, and you remove first, and you remove last. Again, the offer, peek, and poll return special values, whereas the add, get, and remove throw exceptions. In addition to being able to iterate through things, it has two iterators, so you can run from the front to the rear, or you could run from the rear to the front. And you can call iterator or descending iterator to get the two iterators that will loop over all the things. So what can you do with a queue or a deck? Well, since it extends queue, you can use it as a queue. You just ignore the add front and rear. You just decide I'm going to add to the rear and add to the front and use it as a queue because it extends queue. You can also use it as a stack because we can get to the front and add to the front or add to the rear and remove from the front and remove from the rear. So you could just say push is the same as add first, right? Yeah, add first. And then pop is just remove first. And then peek is just peek first. So you can look at the front. Since you can add to it, that's just like pushing onto the stack. And you pop and peek just like you did before. So you can use a deck as a stack. Whereas the stack class in Java it extends vector, so it's got all these weird methods that you really don't want. Again, deck extends all these methods, so as long as you only use 3 of them, the right 3, then you can implement a stack. And also the empty method is just the isEmpty method. So that's this very quick overview of a deck. It's a double-ended queue. Thank you for your attention.